All right, today we're going to do a design review of the Ultra4 slash rock bouncer, whatever this thing morphed into. And we're just going to start from front to back and go over some aspects of the design, some of the design choices that I made, some of the components that I used, and some SolidWorks tips and tricks and tutorials for how to make an assembly like this with functioning suspension travel. So whenever I first started thinking about this design, the idea behind it was to do a design study on what would happen if you took a Can-Am Maverick R and scaled it up to have a full-size engine and the biggest tires that are commercially available. So the interesting thing to me about this Can-Am Maverick R suspension is the tall knuckle design. I've never seen anything like this. And when you first see this design, it looks so strange and out there. You have this upper control arm going up and around the top of the wheel. And the more I learned about this design, the more interesting it became, because what they have here is super unique. So you have the center of the hub about here, and then the lower control arm mount down here, and the upper control arm mount up there. And this line between the upper control arm mount, the lower control arm mount, and the center of the hub is called the Kingpin inclination angle. And I learned about this from a really great video from the guys at Shock Therapy. They have a ton of videos explaining suspension geometry and off-road vehicle design. And this term, Kingpin inclination angle, is a specification in automotive engineering. And the reason it's called an inclination angle is because on a normal vehicle, it's tilted like this. So you can imagine if this was a normal or even the previous version of the Can-Am, they would have a hub and then two A-arms here. And then the angle between this upper control arm mount, this lower control arm mount, and the center of the wheel is your Kingpin inclination angle. And it's usually tilted like that. And the reason that's important is because the distance between the center of the wheel and the intersection point of this Kingpin inclination angle is called scrub radius. And the reason that's important is while a vehicle is cycling through its suspension and cycling through steering, this pivot point is not perfectly in the center of the tire. But on the Can-Am design, this angle is straight up and down, which gives you a lot of advantages when it comes to handling. And this is also the reason why they have this great big tall knuckle here. That's what they call it. And it's this piece that captures the wheel hub and then reaches up and around the tire to interface with that upper control arm. And what's really interesting about this design is that it reduces the point loads on all the pivot points. And it took me a while to really understand what they mean when they talk about that. But you can imagine if there's a force on the bottom of this tire, the distance from the bottom of the tire to the upper control arm mount is a moment arm acting on the ball joints. And the shorter that moment arm is, the more force you have on the ball joints. So if you can increase that distance as much as possible, it reduces all the stress on the pivot points significantly. So on the old design, this distance is really short, like maybe 6 inches or so. And then on the new design, let's say you're going through a turn and you hit a big rock and it's going to induce a force load on the side of the tire near the bottom. Your new moment arm is really long. So it just makes it incredibly strong. The other thing that I really like about the Can-Am Maverick R design is that they include a tall knuckle in the rear as well. It doesn't quite reach up and around the tire in the same way because that's only necessary for the wheels that are steering, and there's no rear steer on this, but you still have that same moment arm force reduction on this top control link in the rear. And so a couple months ago, I was riding around in Moab on my dirt bike, and I was with some buddies who had rented a bunch of side-by-sides, and you could see the difference in the handling between the new Can-Am suspension design and the legacy side-by-side suspension designs. These things are just unstoppable. The other thing that I got really interested in was portal hubs. This is a design from a company called 74 Weld, and they make race portals for trophy trucks. They also have a bunch of really cool portals for OEM applications like on Tacomas and 4Runners. And the advantage to a portal is, just like on a Humvee, you gear down at the hub. So you're reducing the stress on your gears and your axles out at the wheel rather than just relying on the diff. And so once I started thinking about what I wanted to do with this design, it was clear to me that I wanted to run portals in conjunction with this tall knuckle design because that would allow me to run the biggest tires possible, which are these Mickey Thompson Baja Pro XS. These are 58-inch tires, and these are the biggest tires that anybody's ever made. And so I've always had this idea in my head especially in off-road racing applications. Why limit yourself to a 40-inch tire like you see on most trophy trucks? Maybe that's a rule book thing where they're limited in terms of tire size, but I think these guys are inching their way up, like 41, 42s. And if you've been following Baja for a long time, like since the inception, these guys used to run 35s and people thought it was crazy. And then they went to 37s and everyone thought that the people running 37s were out of their minds. So when you see a tire like this, a BFG Baja TA, this is like one of the most iconic Baja tire shapes there is. That tread pattern is instantly recognizable. And these are like 37s or 38s. And this is what they've been running for a really long time, but they're inching their way up. So why not find the limit of tire size that you can run? Now, a 58-inch tire, that's a lot of rubber. It's going to be really heavy. I think it specifies this tire as weighing like 250 pounds or something like that. So it's a lot of weight to be bouncing up and down on the end of a suspension assembly. And it's a lot of radius to be turning. So that's why I wanted to go with the tall knuckle and the portal design, because the tall knuckle decreases the stress from this giant tire. And the portal hub decreases the torque on the axles from turning this giant tire. So really the only guys that run stuff this big are rock crawlers. I don't even think the rock bouncer guys use these. Rock bouncer guys will use 44-inch tires like the Super Swampers, or there's these really cool ones from Kryptonite. Yeah, so these are 46s from Kryptonite, and it's a super sticky compound. They're really big. A lot of guys carve them out to make them lighter. And these are 185 pounds. It's pretty heavy. And there's a saying in off-road racing, bigger tires are the only way to make the bumps smaller. So that's what I wanted to do. That's what this design study was all about. I wanted front and rear independent suspension, which the Ultra4 race vehicles are sort of pushing the boundaries of IFS and IRS. And I wanted to scale up that Can-Am tall knuckle design because I think that's pushing the limits of suspension geometry design at the moment. And I wanted to use portals. That was the idea behind this vehicle. And so I started off calling it an Ultra4, but I'm not a race guy. I don't like going around a track a zillion times. I'd rather go exploring on trails, and I have a family. So I wanted to make a big 4-seater with the craziest suspension I could conceptualize and the biggest tires I could find. And so take a Can-Am 4-seater, scale it up, put a big motor in it, and see what you get. And what I ended up with was this: IFS, IRS, giant tires, portals, tall knuckles, and a rock bouncer style tube chassis because they just look so cool. So now let's dive into the portal hub gear design. So working from the outside in, I decided to go with F250 style unit bearings. The main advantage being it's an 8-lug pattern. It's incredibly strong. There's a lot of wheel options available because those Mickey Thompsons at the 58-inch tire size, they require a 24-inch rim. And so I designed up a set of custom bead locks for that. But I don't know a ton about wheel design. I'm sure I did something incorrectly, but it's a mock-up for someone who actually knows what they're doing with wheel design because that's pretty complicated. But the unit bearing and everything after that, I'm pretty confident in. So the unit bearing bolts to this portal hub shell, and the portal hub shell captures all these gears in relation to the tall knuckle. And so I took a lot of design inspiration from the guys at 74 Weld. They're pretty great if you reach out and have questions. And this gear design went through a couple of iterations before I landed on this, which is a 2-to-1 gear reduction. So you can imagine this is the input shaft, which attaches to this input gear. And then these two gears on the outside are identical, but they're idler gears, which means they're just riding on bearings. They're just transferring the power from the input shaft to the output shaft. And then the output shaft, its gear diameter is twice that of the input shaft. So that's how you get your 2-to-1 gear reduction. So I don't know what the trophy truck guys run. I imagine it's probably 1.5 or something. But since these tires are gigantic, it was really important to me to keep a 2-to-1 gear reduction, because if you have a 2-to-1 gear reduction on the hub and then a standard 5-to-1 on the diff, then you can run a race transmission, and then with the hub reduction, it allows you to run a standard diff without having a crazy 10-to-1 diff or something like that. You can have a regular 5-to-1 diff and then 2-to-1 at the hubs, and then you have the right wheel speed. And then bearing selection here is something that's really important. I found all these bearings on McMaster. This is a tapered roller bearing, and when you look at the cross-sectional profile of a tapered roller bearing, you notice a ramp between the race and the rollers. And the advantage that gives you is you can have a lot of thrust force on this bearing and it's going to stay really strong. The disadvantage is something like this has to be preloaded so that you have the right contact force between the rollers and the race. but this is the biggest one I could find on McMaster. It has a 4-inch inner diameter and a 6-inch outer diameter, and it matches perfectly the gear size that I needed. And then on the input shaft and the idler gears, I'm using smaller tapered roller bearings, and so I'm pretty confident in this design. The only thing that I don't know about is gear teeth design, which is its own rabbit hole, and it's really complicated, and there's a lot of experts out there, and I'm not one of them. So this would be something that I would hand off to a real mechanical engineer who can do gear teeth design to make sure that everything meshes properly, has the correct amount of backlash, and has enough spacing between the teeth so that you can get oil in between the faces that are moving. But then the tall knuckle, this is the most complicated part on the whole vehicle, and this is what I started with. And this is the second or third iteration of this, and it has to do a lot of things. It has to capture the input shaft from the axles. It has to hold the gears. It has to seal around the portal shell hub, and it has to capture all the suspension components, including steering. So what you see down here is a spherical bearing from McMaster. Again, one of the biggest ones I could find. And these spherical bearings are about 50% bigger than any of the Heims that the trophy truck guys use. This is getting into rock bouncer territory in terms of spherical bearing size, because there's just so much force coming from those gigantic tires that I wanted to scale everything up to match. And so one subtlety of something like this is that the spherical bearings, as they come, don't have enough angle deflection for the steering angle that's needed. So I have these custom misalignment spacers, which would be machined and then heat treated out of stainless steel. And this allows you to get more movement out of the spherical bearing. And then a great big bolt coming through, a grade 8 bolt, and then these heat treated inserts, because you have steel here, steel on the bolt, and then you have aluminum on the housing. So you don't want the steel to be rubbing on the aluminum because it's going to gall and open up those holes and tear everything apart. So these heat treated inserts solve that problem. So I actually reached out to the guys at 74 Weld, and they got back to me about what these parts are, because they're not off the shelf. These are custom machined. They're really simple in terms of their part geometry, but the material selection is really important. It's 17-4 heat treated steel. And then material selection on the tall knuckle is also really important. Not a lot of people run billet hubs or billet knuckles, because you can imagine how expensive this part will be to machine. It's a gigantic piece of stock. It's almost 3 feet tall, and most sane people other than me would just fabricate something like this out of chromoly. But I wanted to stay true to the design inspiration from 74 Weld and use the material that they use, which is 70-75 aluminum, which is similar in its weight properties to the more common 60-61 aluminum. That's that T6 stuff you see everywhere. It's aircraft grade aluminum. 70-75 is heat treated, which makes it almost as strong as steel, but without all the weight. And since this thing has really crazy geometry and really precise components, like all of these bearing housings, it just made sense to make it out of that aluminum. And then on the upper control arm mount, I'm using the same spherical bearing. This is the housing version, in contrast with the spherical swivel, and this is captured with a C-clip. So you don't want to press fit these, so then it won't cycle correctly. You want to slip fit and then capture it with a C-clip. And so with all of the material selections loaded into SolidWorks, this assembly by itself weighs 200 pounds, which is pretty crazy. It almost begs the question, would it be lighter to run solid axles? But that's part of the design study, to answer your questions like that. So the trickiest part of this whole design was getting the steering correct. Most trophy truck hubs have the steering mounts out here outside of the wheel, but when I started with a design like that, what I noticed was that none of the pivot points were lined up, and I got a ton of bump steer, like multiple inches of bump steer. So what that means is when the suspension is cycling up and down, the steering is inadvertently cycling in and out, which you don't want. Some bump steer is okay, but I wanted to get it as close to zero as possible. So I ended up moving the steering in and moving those mounting points in as well. And I'll show you what that looks like. So this is a PSC hydraulic steering pump, which is what the rock crawler guys use. And then I have these rod ends connected to the steering links that attach to the hubs. And the way I have it designed now, there's zero bump steer. So as the suspension cycles up and down, that wheel angle doesn't move at all, which is really nice. But one of the compromises to this design was that I only got plus or minus 20 degrees of steering angle. So if there's any steering experts out there, let me know if that is not enough, because I think it's not enough. if you're a drift guy and you want plus or minus 60 degrees of steering angle, is that going to happen on here? But yeah, let me know what you guys think about steering angle and what the minimum requirement is for an off-road application. A solid axle rock crawler would have 45 degrees of steering because there's a lot more room. But independent suspension, trophy truck, let me know what you guys think. So the next super fun part of this design was designing the upper and lower control arms. So what I have is another piece of billet 7075. You can see that blue color would come from anodize. The reason I did that initially is because I thought this part was going to be really complicated, but it ended up being fairly straightforward. It's a standard symmetrical A-arm on the bottom, and it's got some pocket cutouts for the shock mounts. And so theoretically, a part like this could be redesigned out of sheet metal. And I initially thought that something like this would be way beyond my sheet metal design understanding, because designing in sheet metal is a lot more complicated than just making a billet part and chopping out cuts where you need it. But this is pretty simple. A lot of the Ultra4 lower control arms have a dip in here, and I think that has to do with shock mount location between the pivot points, but I'm not 100% sure. And I found a lot of really cool reference designs out there there's a guy named Dobry Designs who makes suspension components for Jordan Pellegrino for his Ultra4 race vehicle. There's also the infamous Igor at Triton Engineering, who makes some of the craziest stuff I've ever seen. And so between those two guys who are really pushing the limits of off-road vehicle design and suspension components, that's where I got a lot of that inspiration from for this design. So one thing that I realized after the fact is that this part has its cutouts in the wrong direction. So if you imagine like a dinner plate, if you press on the edges of a dinner plate, you can bend it or snap it. But if you put a dinner plate face down, it's quite a bit stronger because the cuts are going in the direction of the force. The reason I did it this way was so that I could have a smooth face on the bottom for this Delrin slider, so that there's no pockets or features to get hung up on rocks. But I think if I was to take another shot at this design, I would move these cuts to the bottom of the part to increase strength and then put a stainless slider on the bottom. But I'm not going to know for sure until I run this part through FEA to see just how overbuilt or underbuilt it is. And so this part has a lot of jobs to do in the assembly. It has to interface with the chassis with these bushings. It has to capture the shock mounts and the hardware for them. And it has to grab the tall knuckle at the bottom using the spherical bearing. So there's a lot of features in this part, but it's pretty flat. And so the material stock size would not be that crazy. It would just be really wide. And this part by itself weighs 140 pounds. So my instincts are to say it's probably overbuilt, and 140 pounds for a lower control arm is probably too much. I wonder how much lighter it would be after I run it through FEA, or if I were to redesign it out of chromoly. So that's sort of one of the themes of this iteration of the design, is that everything is way too heavy. And I think that's just something that happens whenever you make a first draft, is you either have a tendency to underbuild or overbuild. And I have always had a tendency to overbuild because it's hard to get a sense of scale on a computer screen, but this part is 2.5 feet wide and 3 feet long. So for everyone out there commenting way too heavy, you're right. It's way too, everything is way too heavy on this first iteration, but trust that once these parts go through finite element structural analysis, I'm going to whittle away at the parts that are too thick and too heavy and unnecessary, and it's going to be race ready. So another tip and trick for SolidWorks is, how do I get these mounts to move in the assembly and cycle without binding or breaking? And it took me a long time to figure this out, but the way that you do it is with these things called point features. So I'll show you an example. So this is a spherical bearing that I downloaded from McMaster, and its origin is right in the center of the sphere. So if you take the housing, which is supposed to rotate around the sphere, it also conveniently has an origin right in the center. When you put this into an assembly, so your housing is fixed and then your sphere is mated center on center. If you mate the origins to each other, you can do a coincident mate on the origin, and you can say, don't align the axes. Then it will allow it to swivel. But this only works for a part like this, where the origin is in the center of the part. So I can still move the spherical bearing anywhere that I need to within the assembly. So that's great news. Let's say you're working with a rod end. Here's a rod end from McMaster. We're going to mate the housing, and the housing is fixed. This is one of the biggest rod ends you can find on McMaster. Just like everything else, it's about 50% bigger than what they run on trophy trucks and about the right size for rock bouncers. But here's the issue with this model. The origin is down here, not in the center of the sphere. And then same story for the sphere. So if I mate these origins to each other and unselect align axes, now these parts are mated, but they're mated around the wrong point. So that's not going to work. So how do you get around that? Well, in SolidWorks, they have these really cool features under the reference geometry tab in the toolbar. So what I'll do is I'll find a plane and then I'll select the cylinder and then make an axis. And that axis is now on the center of the sphere. So that's great. But now I need a point, which would simulate an origin mate. So there's another feature called point. And so I'm going to select one of the planes again and the axis that I just made. And that's going to put a point right in the center of the sphere. So that's what I always do on spherical bearings. And then if you do the same thing on the housing, I have a point right in the center of the sphere, and then I have another point on the part that I want to mate it to. I can make a coincidence mate here. It will default to not aligning the axes because it's just a point-to-point mate. And now the spherical bearing can swivel any way that it needs to. So that's how I get all these suspension components to mate with each other properly, where they're fully constrained, nothing's going to fly around, but none of the mates are going to break. I'm very fastidious about, I mean, you could call it OCD, but I don't like having rebuild errors in my parts or my assemblies because SolidWorks makes it this really ugly brown color and I just hate it. And I know it's not, something's not right. It is possible usually to get it right. So speaking of rod ends, one other thing that's really important is this concept called rod ends in bending. And so this is a really common issue with off-road A-arm design. This is a really common design in the trophy truck and pre-runner world. And what this is called is a J-arm because it kind of has that curved shape to it. And if you notice up here, these are rod ends up here. So the rod end, the sphere is about there. And then they have the threaded shaft coming out. And you notice these are perpendicular to the axis of the vehicle, the longitudinal axis. So these are transversely mounted rod ends. But let's say there's a force load from the wheel, right? So the wheel hits a bump, as you do. That force gets translated in the other direction to the upper control arm. And then this force gets imparted on the rod ends. What you have is a force that gets translated from this pivot point to these rod ends. So the first one, it's not so bad, but the second one is at this crazy angle. So the force direction doesn't care what shape this J-arm is. This is a really strong looking shape, so it itself is going to hold its form, but the force loads on these rod ends are going to be at an offset angle with respect to the axis defined by their threaded rods. And so what this phenomenon is called is rod ends in bending. So in a perfect world, these rod ends would be angled in the same direction of their force so that the spherical bearing here and the spherical bearings on the rod ends all draw the same line to each other. But most people don't do this because it makes the design a lot more complicated because then you have two different angles. It's going to make it really hard to adjust the camber angle in and out, but it's the optimal design. That's what I wanted to do on my upper control arm. So there's a lot going on here, but what I have is this big billet piece, which is the upper control arm mount. And then this is the upper control arm here. The reason this has a big kink in it is because when the suspension is cycled fully up, that tall knuckle would interfere with it. And then I have a big cutout on the top for the steering. So this is a super wacky shaped part. But like I was saying before, the force loads don't care what shape part is. As long as the part is strong enough to take the force loads, there's a continuous line between these spherical bearings and the rod ends. So now you can imagine there's a force on the wheel, it gets imparted up to the upper control arm mount through the tall knuckle, and it gets transferred from the spherical bearing to these rod ends. And the great thing about this design is that these lines are all straight between the rod ends and the spherical bearing because the rod end housings are strongest along the axis of their threads, which are this way. And if you have these misalignment spacers in here, you can get the right deflection angle for these weird mounting angles. And it's as strong as it can possibly be in terms of hardware configuration. That's another reason I made this upper control arm mount out of billet. For most applications, you would just have a piece of chromoly plate to capture these, but these are at really strange angles with respect to each other, and they need to be really, really precise locations to make sure everything cycles without binding. And the other advantage is you get to have this really cool piece of billet candy right on the top of the front of the vehicle, which is the most prominent. So that's what I decided to go with for this. So since these angles are pointed at the center of that spherical bearing, you can still adjust them in and out to get the right camber that you need on the wheel. So there's some adjustment built in here rather than on the lower control arm. You don't really need camber adjustments down there. So I just have these bushings. So these are hard mounted to the chassis. So in terms of shock package, for this vehicle, I have a standard coil carrier and a bypass shock. These are King 4.5 inch, which I think is the biggest they make. I know a lot of guys are running the Fox live valve shocks. Those are super cool for race applications, but for a trail buggy like this, regular old shocks, big ones, will be just fine. So I have a coil carrier, a bypass shock, and then a bump stop. And these are really cool. These are new from King. They're piggyback reservoir bump stops. Most bump stops are just regular smooth tube shocks, but these ones just look really insane. And what I have here is this gold piece that's connecting everything together. It's called a slapper arm. And so the advantage to this is as the suspension cycles, the angle of the bump stop can change. And the mates are a bit messy in SolidWorks, but the idea is when the bump stop is fully extended, it's going to land on the lower control arm here. And I have a limit mate between these components. So the distance between this component and the lower control arm, its minimum can be 0 and its maximum can be whatever. And that's a limit mate. So rather than just like a contact or a tangent or some other kind of mate, it's a mechanical interface. So as this lower control arm cycles up, it contacts the bump stop and it goes all the way up with it. And so they call it a slapper arm because it slaps on top of the part that it's interfacing with. The advantage is this bump stop, the angle is variable. So it's never going to scrub or rub on the part that it's touching with. It just follows it smoothly all the way up to the top of the bump. And so that's a huge advantage because most bump stops are mounted at a fixed angle and you have to really be careful about where you put it, what it touches, and whether it can rub without breaking stuff. But these slapper arms are becoming more and more popular. And it was kind of the perfect use case for something as complicated as this, because there's a lot of stuff jammed in here in a tight area. And this wheel moves almost 3 feet in wheel travel in the front. And so to get that bump angle right would be really challenging, but the slapper arm just makes it perfect every time. So that wraps up the front suspension. Let's dive into the rear suspension. So the most important aspect of off-road vehicle design is this idea called instant center and anti-squat. So this is a great video, highly recommend, explaining exactly why this works the way that it is. But basically the idea is you want the pivot point to be in front of the center of gravity of the vehicle. This is why trophy trucks are so heavily weight biased in the rear. It allows the front to float over the bumps and the rear to remain in traction as it's cycling through the suspension up and down without bucking the vehicle up in the air. And so one thing I was really mindful of during this design process was where my center of gravity is. And it was not that challenging to get it in the right spot because it's a mid-engine design, but I'll draw for you what it looks like to have the correct anti-squat and instant center. So here's our center of gravity right here, right where we want it. And then this is the pivot point of the trailing arms. If you draw a line from the bottom of the rear tire through this pivot point, what you get is an intersection line in front of the center of gravity, which is what you want. If the center of gravity was over here, then when you go over a bump, the driving force from the wheel into the vehicle would bucket up and over the center of gravity. This is why a lot of side-by-sides flip when you're going over a jump, because their trailing arms are not that long. And so when you hit a bump, it just bucks the vehicle up in the air. This is another reason why the original iteration of Class 1 buggies put their engines in the back. So these Class 1 buggies dominated Baja forever until trophy trucks came along. And it's kind of, I mean, it's hard to tell from something that looks as crazy like this, but this is an evolution of a VW bug, like a Baja bug, where the engine's in the back. You have these little trailing arms, and then everything else is just like custom tube work around it. That's where they originally started racing in Baja, was these VW bugs with crazy suspension. But if you look at the pivot point here and we draw that line for the instant center, it's pretty steep. So that means something like this, the center of gravity needs to be behind this line, like back here. And the only way to do that is to keep the rear weight bias by putting the engine back here, just like in the old Baja bugs. And so again, it allows the front suspension to float, and it allows the rear tires to stay planted without bucking the rear up in the air. So this is an independent suspension design. The same principle applies. But when you look at trophy trucks, they have these crazy long trailing arms. Part of the reason for that is they allow the rear axle to droop down really far. But the hidden reason behind that is you want that instant center to be in front of the center of gravity. You want the center of gravity to be back here. So this is where I departed from the Can-Am rear suspension design. So this is the back of the vehicle. I have a mid-mounted engine, reverse mounted, with the transmission pointing forward, and then the primary driveline goes to the front diff. Then I have a transfer case going to the rear diff, and then a relay housing to get it back to the center. And then I have full independent suspension. So the diff is fixed in space. There's no live axle back there, but I still have these crazy long trophy truck arms. These are 72 inches long, which is pretty nuts. But I needed that length to get the instant center in the right place so that I have the right anti-squat and the right vehicle dynamics. So this is totally different from anything I've seen before. The Can-Ams use a really complicated set of multi-links, and then the trailing arm captures the hub, so it's sort of all tied in together. On this one, I wanted to use the same portal hub tall knuckle design in the front and the rear. So this assembly is identical to what's in the front, and then the links are just different. So rather than A-arms, I have a trailing arm, and then these are called radius links, the upper and lower radius links. And so this is another big piece of billet 7075, and then another one at the top. And so all of the force loads from the tire are going to go through the wheel, into the radius link, and then into the trailing arm, and then work their way up into the shock. So this is the load bearing component. This upper link just constrains the top of the tall knuckle. But again, since that moment arm is reduced so much, these do not need to be as beefy as the other ones. So I'll show you what that cycling looks like. So as the suspension droops down, again, I have almost 3 feet of suspension travel in the rear. The only limit here is this axle, but this trailing arm rotates within this housing on the radius link, and then all the force goes up into the shocks. So standard coil carrier and bypass shock with another bump stop and a slapper arm. And then these parts are just keeping everything oriented in the right direction. So then as the wheel comes back up, that slapper arm is going to contact the top of the trailing arm, and then the bump stop engages. So that's super cool. And then what this design allowed me to do is get away with using fewer links than what's found on the Can-Am. They have 2 sets of links here. This is just a caster adjustment link. So it would be possible to put a steering pump on here, and then you have rear steer as well, but that's crazy complicated and it didn't seem like the right move for this, but it is possible. And then all these components are constrained along their movement. And this is a totally new independent rear suspension design that I've never seen before. And it allows yet another giant piece of billet candy for the trailing arm. So these trailing arms typically are made out of 4130 chromoly, and they're fabricated. More and more people are starting to run billet trailing arms. Particularly, I'm thinking of guys like Kibitech and some of the pre-runner guys. But I think these are going to become more and more common because it's sort of a known quantity of how strong it is, because you can run it through FEA in a way that you can't really do that with sheet metal, at least not in SolidWorks. At least I don't know how to do it. But a big piece like this is going to be incredibly strong, incredibly precise, and it takes a lot less time to cut something like this out than it does to hand fab a big old trailing arm. But again, just like the rest of this design, it's probably way too heavy. This arm by itself weighs 100 pounds. That's a lot of aluminum. It's definitely overbuilt for the force loads that it's going to be taking, but we'll find out when I run it through FEA. So you can see all the mounts here. So I have pocket cutouts for the shocks, the coil carrier, and the bypass. I have a pocket cutout for the sway bar, which we'll get into next, and then the bump stops. So this is a pretty standard sway bar that I have here. I just mounted it in a different location. So the sway bar attaches to the trailing arms as close as possible to the rear axle. And then there's these sway bar arms and then a torsion bar in between them. And the torsion bar is captured by the chassis. And most trophy trucks with a solid rear axle, they have these sway bar arms flipped the other direction and they attach to the rear. But the reason I didn't do that is because I wanted to put the spare tire back here in a way where it's movable and can swing down, and there's plenty of room up here for it. Now would be a good time to dive into the rear spare tire. So since this tire is so big and so heavy, it weighs 250 pounds, just the rubber by itself. I don't imagine having gas struts strong enough or lifting it by hand. So I had this idea of putting it on a pivot that you can swing, and when the vehicle's on jacks, this contacts the ground. And I have it mounted upside down so that you can access the bolts, the lug nuts, and just unbolt it. And so using the rear winch, you can attach your winch line to this D-ring. Probably want to get rid of this LED light bar because the winch line would come down and around, and then when you engage the winch, it would just pull this thing up and over like that. Then the question is, how do you get it back up? I don't really know. Hopefully you have a buddy, or maybe I could do some sort of contraption with the front winch where the winch line goes up and around the top of the vehicle, but I don't know. So that's the spare tire. Originally, I had this 8-into-1 exhaust going through the spare tire, but a lot of people pointed out very accurately that that would make the spare tire a zillion degrees and it would be impossible to change it. So now I just have this Stinger exhaust coming up. The other issue was with the first iteration of the exhaust, it was coming right through here and there was no place for the fuel tank to live. So now I just have this Stinger exhaust and then this fuel tank. So here's another SolidWorks tip coming your way. This is an 8-into-1 equal length header exhaust, and there's a lot of advantages to that, primarily exhaust scavenging. So the idea is that each pulse of the exhaust is drawn out by the one before it if they're equal length. And so it's like a free torque increase without having to add any turbos or anything. And this is a supercharged Hemi because I wanted really fast throttle response on this off-road vehicle, and turbos are not ideal for desert racing where it's really, really hot. Whereas supercharged engine, you could do water injection, you could have an integrated intercooler, and you have that instant throttle response without super hot turbos or turbo lag. And so the way that you get equal length headers is, it was a lot easier than I thought. There's a lot of space in here to do this, but what you do is you just make a 3D sketch that defines the trajectory of the exhaust through space. And if you select each part of the line, so select this one and then control select all the other ones, this one, that first curve, that first runner, that second curve, that second runner, and then the final curve, and then where it interfaces with the flange of the collector. If you select all of those arcs and lines and then use your measure tool, you get a total length in inches. And so all you have to do to make equal length headers is just count each line path and make sure that they're all the same total length. I think these ones were within 0.1 inches of each other, which is as good as I'm going to make it. But that's how you do that. And then once you have those 3D curves, then you use the weldment feature to define the exhaust pipes, and that's really fast. So that's how you do equal length header design in SolidWorks. So I guess the next thing to talk about is the chassis design. So let's go ahead and dive into what I did when it came to making this chassis. So when I was designing this vehicle, I started with the front suspension, then I put in the seats, then I made the rear suspension and the engine and the drivetrain and all that. And then I saved the chassis for last because I wanted to have all the mounting points for the suspension in there and then build the chassis around it. So these parts here are the shock mounts. This is the sway bar mount. This is for the trailing arms and the radius links. And this is that crazy billet upper control arm mount. And so I'm using 4130 chromoly everywhere. This part by itself ended up being about 2,500 pounds. So it's definitely overbuilt at this point. I used probably too big of tubes in too many places and too many tubes all over the place. That's for sure. So the main chassis rail is 2.5-inch diameter, 1/4-inch wall tube. And I have that a couple of other places as well. And it's probably unnecessary. That's the largest tube size that anybody uses in the rock bouncer world. And then I have a couple of other tube sizes that were dictated by the rod end selection that I used and sway bar tube that I used. But basically all I did here was define my points where the suspension is going to mount, built mounting plates around that, and then just started making 3D sketches. So I started with a side profile where I was referencing a design from a rock bouncer. So a lot of curves, a lot of wild shapes, and it ended up looking really cool. And then I just make a 3D sketch, one big 3D master sketch that ties everything together. And you can see it was really hard to not get lost in the sauce with this thing because there's so many dimensions and so many features that interface with each other. It was a really complicated design. I have a whole video about that design process. But in terms of SolidWorks tips and tricks, if you want to make something like this, all you need is a 3D sketch and a weldment feature. So 3D sketches are kind of tough to get the hang of because you're drawing with a two-dimensional mouse pad on a two-dimensional screen in a 3D virtual space. And you can imagine how hard that is. But once you get the hang of how the sketches behave in relation to each other, you can really make something that looks really beautiful. And then once you have that 3D sketch laid out, the weldment feature gives you these structural tubes that follow the arcs of those lines in the 3D sketch, and they automatically cut them and cope them. Now you can see there's some rebuild errors here where they don't quite interface with each other properly and the coping joints are not quite perfect. So this would be something that you'd have to revisit and make sure that all of your lines are in the right spot, all of your tube cuts and notches are in the right spot. But you end up with something like this, which is super cool. And so one other, I guess the last tip and trick for SolidWorks is making sub-assemblies in the right place. So something like this, it's not a very complicated sub-assembly. There's not a lot of stuff in here, but what there is all the parts that are fixed. So none of these parts move in relation to each other. The tube chassis is fixed, the spherical mounts are fixed to it, and so is the hardware. And it makes file management a lot simpler. And then I have a sub-assembly within the sub-assembly in the form of this upper control arm mount where all of these pieces of hardware bolt to this piece of billet. And so it's kind of a small sub-assembly. It's only a few parts, but it makes it a lot easier to manage and edit and move things around and make sure that your mates are all in the right place. And so you can see just how many mates are in here. There's hundreds of mates in this sub-assembly for not that many parts because there's so much hardware. And if I had all of these mates in my upper assembly, if I had a rebuild error somewhere, it would be really hard to chase them down to figure out where they are. Whereas something like this, all the hardware is fixed, and so nothing needs to be moving and none of these mates should ever break. And then in my upper assembly, I still have a ton of mates in here, but the only mates that are in here are with components that are moving with respect to each other. So I have all my suspension component mates, front and rear, and then the only other mates are the ones that are holding the drivetrain in place with respect to the chassis. And so what I also like to do is make sure that the origin of each assembly is referenced off of something that's common. So usually what I'll do is I'll make the front center of the diff the origin of the assembly. So front plane is the front of the vehicle at the center of the diff. Top plane is the center of the diff. And then the right plane is the center of the vehicle. And then rather than, as I'm building the assembly, I can drop a part into space, mate it off of the planes rather than mating it off of components that might not exist yet. And so that's how I got these suspension components in here before the chassis was built. I actually put these spherical bearings in the upper assembly, fixed them in space with relation to those planes, and then built the chassis around them. And then once the chassis was built, I moved them into the chassis assembly. I delete those plane mates and now they're fixed. And so this is the fewest amount of rebuild errors and the highest amount of moving components I've ever had in an assembly. So that process really does work. So that's going to wrap up the vehicle design review for whatever the heck this thing is. Let me know what you guys think I should call it. The Ultra4, the Rock Bouncer, the Ultra Bouncer, Crazy Egg, whatever this thing is, the giant side-by-side. Yeah, curious to hear everybody's take. Been getting a lot of really great feedback and encouragement from everyone who is interested in following along this design process. So thank you to everybody who has taken interest in this thing that has lived in my head for years, and now it gets to live on your computer screens, and hopefully it can live in the real world someday.